This video introduces JSON. Let's start by talking about its pronunciation. Some people call it JSON and some call it JSON. I did a little bit of investigation and discovered that the original developer of JSON calls it JSON, so I'll do that too. Like XML, JSON can be thought of as a data model, an alternative to the relational data model that is more appropriate for semi-structured data. In this video, I'll introduce the basics of JSON, and I'll also compare JSON to the relational data model, and I'll compare it to XML. But it's not crucial to have watched those videos to get something out of this one. Now, among the three models, the relational model, XML, and JSON, JSON is by a large margin the newest, and it does show there aren't as many tools for JSON as we have for XML, and certainly not as we have for relational. JSON stands for JavaScript Object Notation, although it's evolved to become pretty much independent of JavaScript at this point. The little snippet of JSON in the corner is right now mostly for decoration. We'll talk about the details in just a minute. Now, JSON was designed originally for what's called serializing data objects. That is, taking objects that are in a program and sort of writing them down in a serial fashion, typically in files. One thing about JSON is that it is human readable, similar to the way XML is human readable, and it's often used for data interchange. So for writing out, say, the objects in a program so they can be exchanged with another program and read into that one. Also, just more generally, because JSON is not as rigid as the relational model, it's generally useful for representing and for storing data that doesn't have rigid structure, that we've been calling semi-structured data. As I mentioned, JSON is no longer closely tied to JavaScript. Many different programming languages do have parsers for reading JSON data into the program and for writing out JSON data as well. Now let's talk about the basic constructs in JSON. And as we will see, these constructs are recursively defined. We'll use the example JSON data shown on the screen, and that data is also available in a file for download from the website. The basic atomic values in JSON are fairly typical. We have numbers, we have strings, we also have Boolean values, although there are none of those in this example. That's true and false, and null values. There are two types of composite values in JSON, objects and arrays. Objects are enclosed in curly braces, and they consist of sets of label value pairs. For example, we have an object here that has a first name and a last name. We have a more bigger, let's say, object here that has ISBN, price, edition, and so on. When we do our JSON demo, we'll go into these constructs in more detail. At this point, we're just introducing them. The second type of composite value in JSON is arrays, and arrays are enclosed in square brackets with commas between the array elements. Actually, we had commas in the objects as well. And arrays are lists of values. For example, we can see here that authors is a list of author objects. Now, I mentioned that the constructs are recursive. Specifically, the values inside arrays can be anything. They can be other arrays or objects, base values. And the values making up the label value pairs in objects can also be any composite value or a base value. And I did want to mention, by the way, that sometimes this word label here for label value pairs is called a property. So just like XML, JSON has some basic structural requirements in its format, but it doesn't have a lot of requirements in terms of uniformity. We have a couple of examples of heterogeneity in here. For example, this book has an addition and the other one doesn't. This book has a remark and the other one doesn't. But we'll see many more examples of heterogeneity when we do the demo and look into JSON data in more detail. Now let's compare JSON and the relational model. We will see that many of the comparisons are fairly similar to when we compared XML to the relational model. Let's start with the basic structures underlying the data model. So the relational model is based on tables. We set up a structure of tables, a set of columns, and then the data becomes rows in those tables. JSON is based instead on sets, the sets of label value pairs and arrays, and as we saw, they can be nested. One of the big differences between the two models, of course, is the schema. So the relational model has a schema fixed in advance. You set it up before you have any data loaded, and then all data needs to conform to that schema. JSON, on the other hand, typically does not require a schema in advance. In fact, the schema and the data are kind of mixed up together, just like in XML, and this is often referred to as self-describing data, where the schema elements are within the data itself. And this is, of course, typically more flexible than the relational model, though there are advantages to having schema as well, definitely. As far as queries go, one of the nice features of the relational model is that there are simple, expressive languages for querying the database. In terms of JSON, although a few things have been proposed, at this point there's nothing widely used for querying JSON data. Typically, JSON data is read into a program and it's manipulated programmatically. Now let me interject that this video is being made in February 2012. So it is possible that some JSON query languages will emerge and become widely used. There's just nothing used at this point. There are some proposals. There's a JSON path language, JSON query, a language called Jackal. It may be that just like XML, the query languages are going to follow the prevalent use of the data format or data model, but that has not happened yet as of February 2012. How about ordering? One aspect of the relational model is that it's an unordered model. It's based on sets, and if we want to see relational data in sorted order, then we put that inside a query. In JSON, we have arrays as one of the basic data structures, and arrays are ordered. Of course, there's also the fact, like XML, that JSON data is usually written to files, and files themselves are naturally ordered. But the ordering of data in files usually isn't relevant. Sometimes it is, but typically not. Finally, in terms of implementation, for the relational model, there are systems that implement the relational model natively. They're very mature, generally quite efficient and powerful systems. For JSON, we haven't yet seen standalone database systems that use JSON as their data model. Instead, JSON is more typically coupled with programming languages. One thing I should add, however, is that JSON is used in NoSQL systems. We do have videos about NoSQL systems. You may or may not have watched those yet. There's a couple of different ways that JSON is used in those systems. One of them is just as a format for reading data into the systems and writing data out from the systems. The other way it's used is that some of the NoSQL systems are what are called document management systems, where the documents themselves may contain JSON data, and then the systems will have special features for manipulating the JSON in the documents that are stored by the system. Now let's compare JSON and XML. This is actually a hotly debated comparison right now. There is significant overlap in the uses of JSON and XML. Both of them are very good for putting semi-structured data into a file format and using it for data interchange. And so because there's so much overlap in what they're used for, it's not surprising that there's significant debate. I'm not going to take sides. I'm just going to try to give you a comparison. Let's start by looking at the verbosity of expressing data in the two languages. So it is the case that XML is in general a little bit more verbose than JSON. So the same data expressed in the two formats will tend to have more characters in XML than in JSON. And you can see that in our examples because our big JSON example is actually pretty much the same data that we used when we showed XML. And the reason for XML being a bit more verbose largely has to do actually with closing tags and some other features. But I'll let you judge for yourself whether the somewhat longer expression of XML is a problem. Second is complexity. And here too, most people would say that XML is a bit more complex than JSON. I'm not sure I entirely agree with that comparison. If you look at sort of the subset of XML that people really use, you've got attributes, sub-elements, and text, and that's more or less it. If you look at JSON, you've got your basic values, and you've got your objects and your arrays. I think the issue is that XML has a lot of extra stuff that goes along with it. So if you read the entire XML specification, it'll take you a long time. JSON, you can grasp the entire specification a little bit more quickly. Now let's turn to validity. And by validity, I mean the ability to specify constraints or restriction or schema on the structure of data in one of these models and have it enforced by tools or by a system. Specifically, in XML, we have the notion of document type descriptors, or DTDs. We also have XML schema, which gives us XSDs, XML schema descriptors. And these are schema-like things that we can specify, and we can have our data checked to make sure it conforms to the schema. And these are, I would say, fairly widely used at this point for XML. For JSON, there's something called JSON schema. And similar to XML schema, it's a way to specify the structure, and then we can check that JSON conforms to that structure. And we will see some of that in our demo. The current status, February 2012, is that this is not widely used at this point. But again, it could really just be evolution. If we look back at at XML as it was originally proposed, probably we didn't see a whole lot of use of DTDs, and in fact not XSDs for sure, until later on. So we'll just have to wait and see whether JSON evolves in a similar way. Now, the programming interface is where JSON really shines. The programming interface for XML can be fairly clunky. The XML model, the attributes and subelements and so on, don't typically match the model of data inside a programming language. In fact, that's something called the impedance mismatch. The impedance mismatch has been discussed in database systems actually for decades, because one of the original criticisms of relational database systems is that the data structures used in the database, specifically tables, didn't match directly with the data structures in programming languages. So there has to be some manipulation at the interface between programming languages and the database system, and that's the mismatch. So that same impedance mismatch is pretty much present in XML, where in JSON it's really a more direct mapping between many programming languages and the structures of JSON. Finally, let's talk about querying. I already touched on this a bit, but JSON does not have any mature, widely used query languages at this point. For XML, we do have XPath, we have XQuery, we have XSLT. Maybe not all of them are widely used, but there's no question that XPath at least and XSLT are used quite a bit. As far as JSON goes, there's been a proposal called JSON Path. It looks actually quite a lot like XPath. Maybe it'll catch on. There's something called JSON Query. It doesn't look so much like XQuery. And finally, there has been a proposal called Jackal for the JSON query language. But again, as of February 2012, all of these are still very early, so we just don't know what's going to catch on. So now let's talk about the validity of JSON data. So JSON data that's syntactically valid simply needs to adhere to the basic structural requirements. As a reminder, that would be that we have sets of label value pairs, we have arrays of values, and our base values are from predefined types. And again, these values here are defined recursively. So we start with a JSON file, and we send it to a parser. The parser may determine that the file has syntactic errors, or if the file is syntactically correct, then it can be parsed into objects in a programming language. Now, if we're interested in semantically valid JSON, that is JSON that conforms to some constraints or a schema, then in addition to checking the basic structural requirements, we check whether JSON conforms to the specified schema. If we use a language like JSON schema, for example, we put a specification in as a separate file, and in fact, JSON schema is expressed in JSON itself, as we'll see in our demo. We send it to a validator, and that validator may find that there are syntactic errors, or it may find that there are some semantic errors. So the data could be correct syntactically, but not conform to the schema. If it's both syntactically and semantically correct, then it can move on to a parser where it will be parsed again into objects in a programming language. So to summarize, JSON stands for JavaScript Object Notation. It's a standard for taking data objects and serializing them into a format that's human readable. It's also very useful for exchanging data between programs and for representing and storing semi-structured data in a flexible fashion. In the next video, we'll go live with a demonstration of JSON. We'll use a couple of JSON editors. We'll take a look at the structure of JSON data when it's syntactically correct. We'll demonstrate how it's very flexible when our data might be irregular. And we'll also demonstrate schema checking using an example of JSON schema. In this video, we'll see a demonstration of JSON data. As a reminder, JSON stands for JavaScript Object Notation, and it's a standard for writing data objects into a human readable format, typically in a file. It's useful for exchanging data between programs, and generally because it's quite flexible, it's useful for representing and for storing data that's semi-structured. A reminder of the basic constructs in JSON. We have the atomic values such as integers and strings and so on. And then we have two types of composite things. We have objects that are sets of label value pairs, and then we have arrays that are lists of values. In the demonstration, we'll go through in more detail the basic constructs of JSON, and we'll look at syntactic correctness. We'll demonstrate the flexibility of the data model, and then we'll look briefly at JSON's schema. Not widely used yet, but still fairly interesting to look at, and we'll look at some validation of JSON data against a particular schema. So here's the JSON data that we're going to be working with during this demo. It's the same data that appeared in the slides in the introduction to JSON, but now we're going to look into the components of the data. It's also, by the way, the same example pretty much that we used for XML. It's reformatted, of course, to meet the JSON data model, but you can compare the two directly. Lastly, we do have the file for the data on the website, and I do suggest that you download the file so that you can take a look at it closely on your own computer. All right, so let's see what we have. Right now we're in an editor for JSON data. It happens to be the Eclipse editor, and we're going to make some edits to the file after we look through the constructs of the file. So this is JSON data representing books and magazines, and we have a little more information about our books than our magazines. So at the outermost, the curly brace indicates that this is a JSON object. And as a reminder, an object is a set of label value pairs separated by commas. So our first value is the label books, and then our first element in the object is the label books and this big value. And the second, so there's only two label value pairs here, is the label magazines and this big value here. And let's take a look first at magazines. So magazines, again, is the label, and the value we can see with the square brackets here is an array. An array is a list of values, and here we have two values in our array. They're still composite values. So we have two values, each of which is an object, a set of label value pairs. Let me mention, sometimes people call these labels properties, by the way. Okay, so now we're inside our two objects that are the two elements in the array. That's the value of magazines, and each one of those has three labels and three values. And now we're finally down to the base values. So we have the title being National Geographic, a string, the month being January, a string, and the year 2009, where 2009 is an integer. And again, we have another object here that's a different magazine with a different name, month, and happens to be the same year. Now these two have exactly the same structure, but they don't have to, and we will see that as we start editing the file. But before we edit the file, let's go and look at our books here, the value of our other label value pair inside the outermost object. Books is also an array, and the array in this case also has just two elements, so we've represented two books here. It's a little more complicated than the magazines, but those elements are still objects that are label value pairs. So we have now the ISBN, the price, the edition, the title, all either integers or strings, and then we have one nested composite object, which is the authors, and that's an array again. So the array again is indicated by the square brackets. And inside this array, we have two authors, and each of the authors has a first name and a last name, but again, that uniformity is not required by the model itself, as we'll see. So as I mentioned, this is actually an editor for JSON data, and we're going to come back to this editor in a moment. But what I wanted to do is show the same data in a browser, because browsers actually offer some nice features for navigating JSON. So here we are in the Chrome browser, which has nice features for navigating JSON, and other browsers do as well. We can see here again that we have an object in our JSON data that consists of two label value pairs, books and magazines, which are currently closed, and then this plus allows us to open them up and see the structure. For example, we open magazines, and we see that magazines is an array containing two objects. We can open one of those objects and see that the three label value pairs, now we're at the lowest levels, and similarly for the other object. We can see here that books is also an array, and we go ahead and open it up. It's an array of 2 objects. We open one of those objects, and we see again the set of label value pairs, where one of the values is a further nesting. It's an array, and we open that array, and we see 2 objects, and we open them and finally see the data at the lowest levels. So again, the browser here gives us a nice way to navigate the JSON data and see its structure. So now we're back to our JSON editor. By the way, this editor, Eclipse, does also have some features for opening and closing the structure of the data, but it's not quite as nice as the browser that we use, so we decided to use the browser instead. What we are going to use the editor for is to make some changes to the JSON data and see which changes are legal and which aren't. So let's take a look at the first change, a very simple one. What if we forgot a comma? Well, when we try to save that file, we get a little notice that we have an error. We expected an end value, so that's a pretty straightforward mistake. Let's put that comma back. Let's say insert an extra brace somewhere here for whatever reason. We accidentally put in an extra brace. Again, we see that that's marked as an error. So an error that can be fairly common to make is to forget to put quotes around strings. So, for example, this ISBN number here, if we don't quote it, we're going to get an error. As we'll see, the only things that can be unquoted are numbers and the values null, true, and false. So let's put our quotes back there. Now, actually, even more common is to forget to put quotes around the labels in label value pairs. But if we forget to quote that, that's going to be an error as well. You might have noticed, by the way, when we used the browser, that the browser didn't even show us the quotes in the labels. But you do, when you make the raw JSON data, you do need to include those quotes. Speaking of quotes, what if we quoted our price here? Well, that's actually not an error because now we've simply turned price into a string, and string values are perfectly well allowed anywhere. Now, we'll see when we use JSON schema that we can make restrictions that don't allow strings in certain places, but just for syntactic correctness of JSON data, any of our values can be strings. Now, as I mentioned, there are a few values that are sort of reserved words in JSON. For example, true is a reserved word for a Boolean value. That means we don't need to quote it because it's actually its own special type of value. And so is false. And the third one is null. So there's a built-in concept of null. Now, if we wanted to use nil for whatever reason instead of null, well, now we're going to get an error because nil is not a reserved word. And if we really wanted nil, then we would need to actually make it a quoted string. Now let's take a look inside our author list, and I'm going to show you that arrays do not have to have the same type of value for every element in the array. So here we have a homogeneous list of authors. Both of them are objects with a first name and a last name as separate label value pairs. But if I change that first one, the entire value, to be, instead of a composite one, simply the string Jeffrey Ullman, oops, sorry about my typing there, and that is not an error. It is allowed to have a string and then a composite object, and we could even have an array and anything we want. In an array, when you have a list of values, all you need is for each one to be syntactically a correct value in JSON. Now let's go visit our magazines for a moment here, and let me show that empty objects are okay. So a list of label value pairs comprising an object can be the empty list, and so now I've turned this magazine into having no information about it, but that is still legal in JSON. And similarly, arrays are allowed to be of 0 length, so I can take these authors here and I can just take out all of the authors and make that an empty list, but that's still valid JSON. Now, what if I took this array out altogether? In that case, now we have an error because this is an object where we have label value pairs, and every label value pair has to have both a label and a value. So let's put our array back, and we can have anything in there. So let's just make it foo, and that corrects the error. What if we didn't want an array here instead and we tried to make it, say, an object? Well, we're going to see an error there because an object, as a reminder, and this is an easy mistake to make, objects are always label value pairs. So if you want just a value, that should be an array. If you want an object, then we're talking about a label value pair. So we can just add foo as our value, and then we're all set. So what we've seen so far is syntactic correctness. Again, there's no required uniformity across values in arrays or in the label value pairs and objects. We just need to ensure that all of our values, our basic values, are of the right types, and things like our commas and curly braces are all in place. What we're going to do next is look at JSON schema, where we have a mechanism for enforcing certain constraints beyond simple syntactic correctness. If you've been very observant, you might even have noticed that we have a second tab up here in our editor for a second JSON file, and this file is going to be the schema for our bookstore data. We're using JSON schema, and JSON schema, like XML schema, is expressed in the data model itself. So our schema description for this JSON data is itself JSON data, and here it is. And it's going to take a bit of time to explain. Now, the first thing you might notice is, wow, the schema looks more complicated and, in fact, longer than the data itself. Well, that is true, but that's mostly because our data file is tiny. So if we had, thousands, tens of thousands of books and magazines, our schema file wouldn't change, but our data file would be much longer, and that's the typical case in reality. Now, this video is not a complete tutorial about JSON schema. There's many constructs in JSON schema that weren't needed to describe the bookstore data, for example. And even this file here, I'm not going to go through every detail of it right here. You can download the file and take a look, read a little more about JSON schema. I'm just going to give the flavor of the schema specification, and then we're going to work with validating the data itself to see how the schema and data work together. But to give you the flavor here, let's go through at least some portions of the schema. So in some sense, the structure of the schema file reflects the structure of the data file that it's describing. So the outermost constructs in the schema file are the outermost in the data file, and as we nest, it parallels the nesting. Let me just show a little bit here. We'll probably look at most of it in the context of validation. So we see here that our outermost construct in our data file is an object. And that's told to us because we have type as one of our built-in labels for the schema. So we have an object with two properties, as we can see here, the books property and the magazines property. And I use the word labels frequently for label value pairs. That's synonymous with property value pairs. Then inside the books property, for example, we see that the type of that is an array. So we've got a label value pair where the value is an array. And then we follow the nesting and see that it's an array of objects. And we go further down and we see the different label value pairs of the objects that make up the books and nesting further into the authors and so on. We see similarly for magazines that the value of the label value pair for magazines is an array, and that array consists of objects with further nesting. So what we're looking at here is an online JSON schema validator. We have two windows. On the left we have our schema, and on the right we have our data, and this is exactly the same data file and schema file that we were looking at earlier. If we hit the validate button, hopefully everything should work, and it does. This tells us that the JSON data is valid with respect to the schema. Now, this system will, of course, find basic syntactic errors, so I can take away a comma just like I did before, and when I validate, I'll get a parsing error. That really has nothing to do with the schema. What I'm going to focus on now is actually validating semantic correctness of the JSON with respect to the constructs that we've specified in the schema. Let me first put that comma back, so we start with the valid file. So the first thing I'll show is the ability to constrain basic types, and then the ability to constrain the range of values of those basic types. And let's focus on price. So here we're talking about the price property inside books, and we specify in our schema that the type of the price must be an integer. So for example, if our price were instead a string, and we went ahead and tried to validate that, we would get an error. Let's make it back into an integer. But let's make it into the integer 300 now instead of 100. And why am I doing that? Because the JSON schema also lets me constrain the range of values that are allowed if we have a numeric value. So not only in price did I say that it's an integer, but I also said that it has a minimum and maximum value. The integer of prices must be between 0 and 200. So if I try to make the price of 300 and I validate, I'm again getting an error. Now it's not a type error, but it's an error that my integer was outside of the allowed range. I've put the price back to 100, and now let's look at constraints on string values. JSON schema actually has a little pattern matching language that can be used to constrain the allowable strings for a specific type of value. We'll look at ISBN number here as an example of that. We've said that ISBN is of type string, and then we've further constrained in the schema that the string values for ISBN must satisfy a certain pattern. I'm not going to go into the details of this pattern matching language. I'm just going to give an example. And in fact, this entire demo is really just an example. There are lots of things in JSON schema that we're not seeing. What this pattern here says is that the string value for ISBN must start with the 4 characters ISBN and then can be followed by anything else. So if we go over to our data and we look at the ISBN number here and say we have a typo, we forgot the I, and we try to validate, then we'll see that our data no longer matches our schema specification. Now let's look at some other constraints we can specify in JSON schema. We can constrain the number of elements in an array. We can give a minimum or a maximum or both. And I've done that here in the context of the authors array. Remember, the authors are an array that's a list of objects. And here I've said that we have a minimum number of items of 1 and a maximum number of items of 10. In other words, every book has to have between 1 and 10 authors. So let's try, for example, taking out all of our authors here in our first book. We actually looked at this before in terms of syntactic validity, and it was perfectly valid to have an empty array. But when we try to validate now, we do get an error, and the reason is that we said that we needed between 1 and 10 array elements in the case of authors. Now let's fix that not by putting our authors back, but let's say we actually decide we would like to be able to have books that have no authors. So we can simply fix that by changing that minimum item to 0, and that makes our data valid again. And in fact, we could actually take that minimum constraint out altogether, and if we do that, our data is still going to be valid. Now let's see what happens when we add something to our data that isn't mentioned in this schema. If you've looked carefully, you'll see that everything we have in the data so far has been specified in the schema. Let's say we come along and decide we're going to also have ratings for our books. So let's add here a rating label or property with the value 5. We go ahead and validate. You probably think it's not going to validate properly, but actually it did. The definition of JSON schema is that it can constrain things by describing them, but you can also have components in the data that aren't present in the schema. If we want to insist that every property that is present in the data is also described in the schema, then we can actually add a constraint to the schema that tells us that. Specifically, under the object here, we can put in a special flag, which itself is specified as a label, called additional properties. And this flag, if we set it to false, and remember false is actually a keyword in JSON schema, tells us that in our data we're not allowed to have any properties beyond those that are specified in the schema. So now we validate and we get an error because the property rating hasn't been defined in the schema. If additional properties is missing or has the default value of true, then the validation goes through. Now let's take a look at our authors that are still here. Let's suppose that we don't have a first name for our middle author here. If we take that away and we try to validate, we do get an error because we specified in our schema, and it's right down here, that author objects must have both a first name and a last name. It turns out that we can specify for every property that the property is optional. So we can add to the description of the first name not only that the type is a string, but that that property is optional. So we say optional, true. Now let's validate, and now we're in good shape. Now let's take a look at what happens when we have an object that has more than one instance of the same label or same property. So let's suppose, for example, in our magazine, the magazine has 2 different years, 2009 and 2011. This is syntactically valid JSON. It meets the structure of having a list of label value pairs. When we validate it, we see that we can't add a second property year. So this validator doesn't permit 2 copies of the same property, and it's actually kind of a parsing thing and not so much related to JSON schema. Many parsers actually do enforce that labels or properties need to be unique within objects, even though technically, syntactically correct JSON does allow multiple copies. So that's just something to remember. The typical use of objects is to have unique labels. Sometimes they're even called keys, which evokes the concept of them being unique. So typically they are unique. They don't have to be for syntactic validity. Usually when you want to have repeated values, it actually makes more sense to create an array. I've taken away the second year in order to make the JSON valid again. Now let's take a look at months. I've used months to illustrate the enumeration constraint. So we saw that we could constrain the values of integers, and we saw that we could constrain strings using a pattern, but we can also constrain any type by enumerating the values that are allowed. So for the month, we've said it's a string type, which it is, but we've further constrained it by saying that string must be either January or February. So if we tried to say put in the string March, we validate and we get the obvious error here. We can fix that by changing the month back, but maybe it makes more sense that March would be part of our enumeration type. So we'll add March to the possible values for months, and now we're good. As a next example, let's take a look at something that we saw was syntactically correct, but isn't going to be semantically correct, which is when we have the author list be a mixture of objects and strings. So let's put Jeffrey Ullman here just as a string. We saw that that was still valid JSON, but when we try to validate now, we're going to get an error because we expected to see an object. We have specified that the authors are objects, and instead we got a string. Now, JSON schema does allow us to specify that we can have different types of data in the same context, and I'm going to show that with a little bit of a simpler example here. So let's first take away our author there so that we're back with a valid file. And what I'm going to look at is simply the year values. So let's suppose for whatever reason that in our magazines one of the years was a string and the other year was an integer. So that's not going to work out right now because we have specified clearly that the year must be an integer. In JSON schema specifications, when we want to allow multiple types for values that are used in the same context, we actually make the type be an array. So instead of just saying integer, if we put an array here that has both integer and string, that's telling us that our year value can be either an integer or a string, and now when we validate, we get a correct JSON file. That concludes our demo of JSON schema validation. Again, we've just seen one example with a number of the constructs that are available in JSON schema, but it's not nearly exhaustive. There are many others, and I encourage you to read a bit more about it. You can download this data and this schema as a starting point and start adding things and playing around, and I think you'll get a good feel for how JSON schema can be used to constrain the allowable data in a JSON file.